ಇದಕ್ಕೆ ಏನಾದ್ರು ಒಂದು ಎಜುಕೇಶನ್ ಹಾಕ್ಬೇಕಲ್ಲಪ್ಪ. And then I first
Good morning, everyone. Myself, Parmeshwar, Assistant Professor at Department of Mechanical Engineering, JNC Shimoga. Department of Mechanical Engineering, JNC Shimoga, is organizing one-week faculty development program on novel non-structured energy-based alloys for industrial and biomedical applications. It is sponsored by ATAL Training and Learning Academy, New Delhi. Now I invite Dr. E. Basavaraj, Head of the Department, Mechanical Engineering, to welcome the gathering and brief about the department.
good morning. A very good morning to all of you. Respected dignitaries on and off the dais, faculty participants from various engineering colleges, IITs across India, industry participants, my colleagues, and media persons. I am privileged to welcome all of you to this inaugural function of 1 week ABCD training and learning ATAL faculty development program on novel nano-structured magnesium-based alloys for industrial and biomedical applications. First of all, I would like to welcome Sri A.S. Vishwanatha, President of National Education Society, to this program. I welcome you, sir. Thank you. On behalf of National Education Society, Jawaharlal Nehru, National College of Engineering and the Department of Mechanical Engineering, I welcome Chief Guest of today's function, Dr. Manoj Gupta, Associate Professor, Department of Mechanical Engineering, National University of Singapore, to this function. I welcome you, sir. I also welcome guest of honor of today's function in his absentia, Sri T.R. Ashwath Narayana Sethi, Vice President, National Education Society. Star, National Education Society, to this course faculty program. I also welcome Dr. P. Manjunatha, Principal, Dean Infrastructure, a professor and coordinator of this ATAL program, to this program. I also welcome all the directors and members of National Education Society to this program. Finally, I would like to welcome participants of this FDP from various academia and industries to this program, and faculty colleagues of our college and the media persons to this program. This is about, now I'd like to brief you about our department, Mechanical Engineering Department. Mechanical Engineering Department started in the year 1980 at the time of inception of our college, and our department has a highly qualified faculty comprising of 10 doctorates and 12 master's holders. Our department is a recognized research center of Visvesvaraya Technological University, and has produced 9 PhDs and another 10 are pursuing their PhD. I am proud that our department has one patent to its credit, that is butt scooping machine, and our department has well-equipped laboratories and trained technical and supporting staff. Finally, I would like to put it on the card that this FDP is the third FDP sponsored program being organized by our department and college. The first is on Blue Ocean Strategy, coordinated by Dr. E. Basavaraj, and the second one on design thinking by Dr. Sabeen Ahmed. I welcome all of you to this program. Thank you.
JNC is an institution under the umbrella of National Education Society, Shivamogga. We have with us the President of National Education Society, Sri A. Sunata. I request him to raise this occasion with his voice. ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. ಇವತ್ತು ಒಳ್ಳೆ ಪ್ರೋಗ್ರಾಮ್ ಮಾಡ್ತಾ ಇದ್ದೀವಿ. ಮೆಕ್ಯಾನಿಕಲ್ ಡಿಪಾರ್ಟ್ಮೆಂಟ್ FDP ಪ್ರೋಗ್ರಾಮ್ ಮುಖ್ಯವಾಗಿ ನಾವು ಏನೇನೋ ಮಾಡಿದ್ವಿ. ನಾವು ಇವಾಗ ಫಸ್ಟ್ ಯಾಕೆಂದ್ರೆ 2500 ವರ್ಷಗಳ ಹಿಂದೆನೆ ನಾವು ಅಶೋಕ ಸ್ತಂಭ ಡೆಲ್ಲಿ ಇದೆಯಲ್ಲ ಅದನ್ನು ಮಾಡಿದ್ವಿ. ಅದಕ್ಕೆ ತುಕ್ಕು ಗಿಕ್ಕು ಇಲ್ಲಿವರೆಗೆ ನಾವು ಅಶೋಕ ಸೀರಿಯಲ್ ಅಲ್ಲ ಅದನ್ನ ನೋಡಿದ್ವಿ. ಬಹಳ ಚೆನ್ನಾಗಿದೆ ಅದು. ಅವಾಗ ಲೀಡರ್ ಇನ್ ದಿ ವರ್ಲ್ಡ್. ಈಗ ಯಾಕೋ ಎಲ್ಲ ನಾವು ಬಿಟ್ಟಿದ್ದೀವಿ. ಈಗ ಬಿಜೆಪಿ ಗೌರ್ಮೆಂಟ್ ಎಲ್ಲ ಸೆಂಟ್ರಲ್ ಗೌರ್ಮೆಂಟ್ ಜಾಸ್ತಿ ಇದನ್ನು ಕೊಟ್ಟು ಈ ತರ ಪ್ರೋಗ್ರಾಮ್ಗಳನ್ನ ಮಾಡಿ ಇಲ್ಲಿ ಹಳ್ಳಿಗೆ ತಲುಪಬೇಕಾಗ ಆಗಿ ಬಂದಿದೆ. ಈಗ ನನಗ ನಮ್ಮ ಪಾಪ್ಯುಲೇಷನ್ ವೈಸ್ ಹ್ಯೂಮನ್ ಸ್ಟ್ರೆಂತ್ ಬಹಳ ಇದೆ ನಮ್ಗೆ. ಅದನ್ನ ನಾವು ಅದನ್ನು ಉಪಯೋಗಿಸ್ಕೊಂಡು ನಾವು ಸರಿಯಾಗಿ ಇದನ್ನ ಮಾಡಿದ್ರೆ ನಾವು ಪ್ರಪಂಚಕ್ಕೆ ಲೀಡರ್ಸ್ ಆಗ್ತೀವಿ. ನಿಜವಾಗ ಅದ್ರೊಳಗೇನು ಅನುಮಾನ ಇಲ್ಲ. ನಮಗೆ ಏನೋ ಇದು ಮನುಷ್ಯ ಮಾನವ ಸಂಪನ್ಮೂಲ ಬಹಳ ಚೆನ್ನಾಗಿದೆ. ಅದನ್ನ ಸರಿಯಾಗಿ ಉಪಯೋಗಿಸ್ಕೊಬೇಕು. ಅದಕ್ಕೆ ಲೀಡರ್ಸ್ ಬೇಕು. ಆಮೇಲೆ ಹಾಗೆ ಗೌರ್ಮೆಂಟಿನ ಸಹಾಯವೂ ಬೇಕು. ಈಗ ಅದನ್ನೆಲ್ಲ ಉಪಯೋಗಿಸ್ಕೊಂಡು ಇದು ಮಾಡ್ಬೇಕು. ಆಮೇಲೆ ಇವತ್ತಿನ ಪ್ರೋಗ್ರಾಮ್ ಅಲ್ಲಿ MG based allies for instrumental and biomedical appliances. ಈಗ ಮೊದಲೆಲ್ಲ ಏನಿತ್ತು, ಸುಮ್ಮನೆ ಕೊಟ್ಟಾಕರು ಅದಾಗೆ ಕೂಡಬೇಕು ಹಂಗೆ ಅಂತ ಇತ್ತು. ಈಗೇನಾಗಿದೆ, ರೈಲ್ವೆ ಸ್ಟೇಷನ್ ಹೋದ್ಮೇಲೆ ರೈಲ್ವೆ ಸ್ಟೇಷನ್ ಮಾಡ್ತಾ ಇದ್ರು. ಅದು ಒಳ್ಳೆ ಚೆನ್ನಾಗೇ ಇತ್ತು. ಈಗ ಏನಾಗಿದೆ, ವಾಚು ಗೀಚಿಗೆಲ್ಲ ಉಪಯೋಗಿಸ್ತಿಲ್ಲ. ಒಳ್ಳೆ ಮೆಟೀರಿಯಲ್ ಅಲಾಯ್ ಮೆಟೀರಿಯಲ್ ಉಪಯೋಗಿಸಿ ಅದನ್ನ ಅದರ ಅಡ್ವಾಂಟೇಜ್ ತಗೊಂಡು ಒಳ್ಳೊಳ್ಳೆ ಎಕ್ವಿಪ್ಮೆಂಟ್ ಮಾಡೋ ಅಂತ ಒಂದು ಕಾಲ ಬಂದಿದೆ. ಅದನ್ನು ನಾವು ಲೀಡರ್ಶಿಪ್ ತಗೋಬೇಕು ಅಂತ ಹೇಳ್ತೀನಿ. ಯಾಕಂದ್ರೆ ಅದು ನೋಡಿ, ಶೂಗೆ ಒಂದೊಂದು ಸ್ಕ್ರೂ ಇಲ್ಲಿ ಸ್ಕ್ರೂ 25,000. ಎಷ್ಟು ಕೊಟ್ಟು ನಿಮಗೆ ಅದು ಎಷ್ಟು ಫೋಲ್ಡ್ ಮೆಟೀರಿಯಲ್ ಜಾಸ್ತಿ ಆಗುತ್ತೆ. ಈಗ ಮೊದಲು ವಾಚಸ್ ಸ್ವಿಟ್ಜರ್ಲೆಂಡಿಂದನೇ ಬರುತ್ತೆ.
ಈಗ ನಮ್ಮ ವಾಚ್ ಫ್ಯಾಕ್ಟ್ರಿ ಆದ್ಮೇಲೆ ಇಂಡಿಯಾದಲ್ಲಿ HMT, ಈಗ ಎಲ್ಲದಕ್ಕೂ ಎಲ್ಲ ಸಣ್ಣ ಸಣ್ಣ ಕಂಪ್ನಿಯವರು ವಾಚ್ ಮಾಡ್ತಾ ಇದ್ದಾರೆ. ಹಾಗೆ ನಾವು ಲೀಡರ್ಶಿಪ್ ತಗೊಬೇಕು. ಅದರೊಳಗೂ ಇಂಜಿನಿಯರಿಂಗ್ ಕಾಲೇಜ್ನವರು ನೀವು ಪಾಠ ಒಂದೇ ಹೇಳೋದು ಅಲ್ಲೇನೆ, ಇದ್ರೊಳಗೆ ರಿಸರ್ಚ್ ಮಾಡೋದು ಫೆಸಿಲಿಟಿ ಅಂದ್ರೆ ಇಲ್ಲಿ ಆಗದೆ ಇದ್ರು ನಮ್ಮ ಕಾಲೇಜಲ್ಲಿ ಬೇರೆ ಕಡೆ ಹೋಗಿ ಅದನ್ನ ಮಾಡೋ ಅಂತ ಒಂದು
ಹಲೋ ಸರ್.
ಟ್ರೈನಿಂಗ್ ಪ್ರೋಗ್ರಾಮ್ಗಳನ್ನ ಮಾಡಿ ಅಲ್ಲಿಗೆ ನಮ್ಮ ಪ್ರೊಫೆಸರು ಸ್ಟಾಫು ಎಲ್ಲ ಹೋಗಿ ಕರ್ಕೊಂಡ್ಬಂದು ಇದರೊಳಗೆ ನಾವು ಹೆಚ್ಚಿನದನ್ನ ಸಾಧಿಸ್ಬೇಕು ಅಂತ ಹೇಳ್ತಾ ನಾನು ಒಂದು ಮಾಡ್ತೇನೆ. ಥ್ಯಾಂಕ್ ಯು.
Thank you, sir. So, especially of India, to speak to your work about the work.
A very good morning to all the resource person and participants in this natural function on novel nanostructure integrates allied for industrial biometric application. It's a very interesting subject in the sense, if you look at the mechanical engineers of my generation, who were passed out in the late 20th century, we always talked about addition of alloying elements to get specific physical and chemical properties. For example, you add silicon and manganese to cast iron and retreat it to behave something like steel, or you add chromium and nickel to steel to become corrosion resistant, become stainless steel. That's all everything we do. And the least measurement that we knew was in my class, that is 10 to the power minus 3. That was the limit when we studied mechanics, power generation. But now with the technical advances, the things have changed. Now we no more talk about the addition of alloying elements, but we talk about nitrates and reinforcement of alloys with nano particles or nano composite particles or whatever you call that. And we talk about the size in nanos, 10 to the power minus 9 and power minus 3 itself was very difficult for us to understand. But now we talk about 10 to the power minus 9 size material. Not at all visible, but to make it happen. So, in that sense, when mechanical engineers of my generation, when we try to read something about this nanomaterials or nano engineering or whatever it is, we feel as though we are reading something chemistry, more chemistry than engineering. So we sleep off. But you faculty members, you cannot afford to do that because you have to learn. I mean, maybe even call this as a professional hazard or whatever it is, but you need to understand and you need to study that, to enhance your knowledge base, those who don't know about the nano materials or nano engineering, or if you know something about the nano engineering, you update your knowledge by attending these sort of workshops and seminars. It's inevitable. I mean, for the mechanical engineering department faculty of these years, it is inevitable that they have to study. So today we are choosing one particular material, magnesium based alloy. Magnesium is a very abundantly available natural element or mineral, whatever we call that. And it has got extensive use in many fields. Nowadays, it's being used in automotive industries also because of its lightweight. The specific gravity is around, I mean, density is less than 2 as compared to the density of steel and cast iron, which is around 8 grams. So it's almost 1/4 of the weight, and that enhances the fuel economy and all those things. Magnesium is the light being used for casting of engine blocks, transmission cases, so many others. But it has its own limitations also, in the sense that it has a low creep resistance, and it is susceptible to corrosion, and you cannot use water-based coolant in that. So many things are there. So we have to overcome all this. So one way of overcoming all this is using the alloying elements, and that to make it usable for everything. Another interesting thing about the magnesium is it's used in medicine also. In biomedicals also it is used. Why? Because magnesium has properties almost similar to gold. It's a it's a biodegradable mineral. So this orthopedics, in orthopedic surgeons started using this. The addition of nano composite particles in that, so that it doesn't degrade faster than bone growth or something like that. So it is being used in the medical field now because of its nature. And so magnesium has both industrial and biomedical use this way. So it is a very interesting element to study, and we have a very interesting program on this particular magnesium alloy. They are very good resource person, internationally reputed resource persons addressing all our faculty members, and I sincerely hope this will be of much use, and this will enhance the knowledge base of the participants and update their knowledge, so that in the end of the day, the students are benefited from these programs. And I wish all the very best to all the participants. Thank you all. Thank you, sir. So request CCR treasurer engineer for the together. Upgrade ಮಾಡ್ಕೊಂತ ಟ್ರೈನಿಂಗ್ ಕೊಡುವಂತ ಪ್ರೋಗ್ರಾಮ್ ಇದಾಗಿದೆ. ಎಲ್ಲ ನಮ್ಮ ಫ್ಯಾಕಲ್ಟಿ ಮೆಂಬರ್ಸ್ ಮಾಡಿ ಒಂದು Thank you, sir. Now I invite the coordinator of this FDP, Dr. M.M. Rajatagade, Dean and Professor, NMC, to brief about the workshop. Good morning, everybody. This FDP is mainly going to concentrate on synthesis and characterization of magnesium-based products for industrial and biomedical applications. As we all know, magnesium is among the lightest element that is seen in the periodic table. It has a density of around 1.7 grams per cc, and it has a very low melting point of 650 degrees centigrade. So that is why it is better used in applications where high temperature resistance is required. So possibly by altering or by adding various elements. For example, adding nickel, adding titanium and strontium to magnesium. Biomedical application is shown very, very promising biomedical application, especially as biodegradable material. As you all know, these implants, when they have to be inserted into the human body, it involves surgery, and the pain, the agony, and the trauma involved in surgery is very huge. So most of the implants that we have today, they have to be removed over a period of usage. Hence, once again, the secondary surgery is required. But these magnesium-based strontium and titanium implants are biodegradable implants, which are permanently implanted in the human body. They do not require a secondary operation, thereby reducing the pain that a patient need to undergo. And especially magnesium, when avoided with the titanium and nickel-based material, its melting point increases. It can be used especially in aerospace applications where the temperature involved is very high. So magnesium nickel-based alloys are finding promising applications. Research is going on, especially in the aerospace application. So some of the techniques of synthesis that are utilized here are non-equilibrium techniques like high pressure torsion, equal channel angular pressing, and PAPA's field activated pressure assisted synthesis. So all these synthesis and characterization techniques will be elaborately dealt in the FDP that we are going to have today. And today, the keynote address will be given by an excellent person in Dr. Manoj Gupta, is professor in the National University of Singapore, and he has readily agreed to be a part of this FDP program by agreeing to give a keynote in a few seconds from now. And in the second session today, we have another excellent speaker in Dr. Svetlana Ilchenko. She is a Chief Executive Officer of Material Science International at Max Planck Institute, Germany. So she has done a lot of work on phase diagram part of the various elements, and she is going to give a talk on magnesium-based binary component, ternary component, and multi-component alloys of magnesium material. So she is a very renowned person in the field of material science. She has conducted some sort of international workshops in Germany. So all these persons, we will be meeting them online in due course of time. So thank you for the opportunity.
It is our pleasure to have Dr. Manoj Gupta, Department of Mechanical Engineering, Singapore, and the chief guest. Now I invite Mr. Pradeep MD, Assistant Professor of our department, to introduce Dr. Manoj Gupta to the audience. Myself, Pradeep of Mechanical Engineering, the Training College of Engineering, Shimoga. Today I am happy to introduce our eminent resource person and chief guest, Dr. Manoj Gupta, Professor of Department of Mechanical Engineering, Singapore. He was a former head of Materials Division of Mechanical Engineering Department and Director Designate of Material Science and Engineering, CCAD of Singapore. He did his PhD from University of California, USA, the year 1992, and postdoctoral research at University of Alberta, Canada, in the year of 1992. He is currently among the 46% researchers as per Stanford youth among the top scientists of the world, position by the Universal Scientific Education, the research network, and among 2.5 among the scientists as per research today. To this, the credit of disintegrated melt deposition technique and ISO microwave sintering technique and energy efficient solid state processing methods to synthesize alloys, micro and the nano composites. There are the published over 600 peer-reviewed journal papers and won 2 United States patents and 1 trade secret. Is the current index is 72, the index is 48.3, and the citation for greater than 18,000. And he is also a author for 8 books and published by John Willis, Springer, and Elmore Williams.
He is also editor in chief and editor of 12 international peer-reviewed journals, a multiple award winner. He actively collaborates with so many countries like Japan, France, Saudi Arabia, Qatar, China, USA, and India as a visiting researcher, professor, and chair professor. Once again, on behalf of the Department of Mechanical Engineering and ATAL FDP, we thank for accepting our invitation, sir. Thank you, Ananda. It's over to you, sir.
I request Dr. Manoj Gupta to inaugurate the FDP and deliver keynote address.
Are you people able to hear me?
Yes, sir. Able to hear you.
Okay, I'm trying to share the screen now. Let me see. Are you able to see my screen?
Oh, yes, sir. Yes, sir.
Yes,
All
sir.
right,
Yes.
perfect. I'd like to thank the team of National Education Society and the team from JNNC to organize this faculty development program and for giving me this platform to share some of the research findings that we have. Now I will start my presentation, which is kind of a new research and direction, which is going in the area of magnesium-based materials. And the title is An Insight into New Generation Magnesium-Based Multi-Component Systems, which is the latest craze now. It gives you additional flexibility to use magnesium-based materials. Okay. All right. So now, if you look at this slide here, you will see that especially in engineering application, you have aluminum, titanium, and steel, which are the workhorses in many application. And if you consider biomedical application, you will have
Screen,
that.
sir.
Yeah,
Sir, please make it full screen, sir.
it is full
In the
screen.
PPT mode. Sir,
It
it should be in PPT mode, sir.
it is PPT
Actually,
mode.
it is in slide mode, sir.
It is in the PPT mode. It's a PPT file. Maybe there's problem, so I'll not go full screen now. Can you see my screen now?
The screen is visible, sir.
Yes, sir. Yes, yes, sir.
Sir, audible.
Okay, so I will go in this mode because many times the problem comes if I go in the full screen mode, the slide does not move. So I will stay in this mode. Are you able to see this slide with the two pictures?
Yes, sir. Yes.
Okay, let me stay in this
Yes,
mode.
sir.
All right, so what you see here is that, as I was saying that aluminum, titanium, and steels are the workhorses of most of the engineering applications. And apparently in biomedical application, yes, titanium is used and steels are used. Now, how does magnesium compares with that? It has a lowest density. That means it can cut down on the fuel consumption more effectively than any of these elements. It has a lowest melting point among these elements. That means the energy for production is limited. So effect on the environment will be minimum in case of magnesium. It has a specific modulus, which is same as other elements like aluminum, titanium, and steels. And it has a specific strength, which is just next to the titanium. But titanium comes at almost 5 times the cost of magnesium. So that makes magnesium a wonderful element. Now, if you focus on the picture on the right hand side, you will see that in this graph, you have strength on the y-axis, and you will see that magnesium in the current state does not show the spectrum of the property that aluminum shows. And aluminum is the next lightweight element which is currently in use. But having said that, it has properties which allows it to replace aluminum, maybe titanium, maybe steel, and maybe nickel. So the biggest challenge at this point of time is to increase the spectrum of the properties similar to that of aluminum so that magnesium and its alloy can find more and more applications. Now, if you look at this graph here, it shows the primary production of aluminum versus magnesium. And at this point of time, Aluminum is 60 times more produced than magnesium, and that shows the potential, upcoming potential of magnesium in the national and international market. That means it can capture a significant number of application, and this is happening, and it will happen at a rapid pace in this decade specifically, because we have to meet that carbon emission requirement as stated by Paris Agreement by 2025. So everyone is gearing towards that. In early part of this century, we have seen some very interesting work from a Taiwanese researcher Jean Wei and Brian Cantor group in UK, and they came out with the concept of high entropy alloys. And we have a big group in India who are working in that as well. Now, these alloys were made using at least five major elements. They called it high entropy alloy, and they classified the alloys based on the configurational entropy. That means if the configuration entropy is more than 1.5 R, then it's a high entropy alloy. If it is between 1 and 1.5, then it is termed as a medium entropy alloy. And if it is less than 1, it is called as a low entropy alloys. Most of the traditional alloys are the low entropy alloys. Many applications were cited for this multi-component system. And if you look in that, light transportation material is one of the stated application where magnesium has a big scope, or I will say the biggest scope among all the metallic elements. Now, over 15 to 20 years, many researchers worldwide have worked on high entropy alloys. And if you look at this table, they made many high entropy alloys, but with a density from somewhere between 11 gram per cc to about 2.2 gram per cc. Most of the research is based on the iron and nickel based, niobium based high entropy alloys. To create multi-component alloys based on magnesium and keeping the lightweight is a challenge, because you don't have many elements that you can add to magnesium, because it itself is one of the lightest weight element. So we came out with the concept of that you call a entropy alloy or multi-component alloy as a lightweight alloy if its density is less than 3 gram per cc. But at the same time, we expect the properties of this material will be much better than the existing materials which are in the market. So like everyone, we also try to look at the high entropy alloys based on magnesium. We use two methods. One is a liquid phase method. What is casting is one of the uh, commonly known liquid phase method, and solid phase methods, and powder metallurgy is one of the very common solid phase method. Now, if you look at this slide, we created this liquid phase method, which is called as a disintegrated melt deposition technique. And in this technique, what we do here is that we take the material into a crucible and we stir it. We use a resistance heating furnace because magnesium has a low melting point at 650 degrees centigrade. We pour this material, it's called as the bottom pouring here. And before it deposits down, we heat it with argon gas jets to increase the heat transfer. Once you increase the heat transfer, you can realize microstructural refinement. The picture on the right hand side shows a typical equipment that we have, and these are some of the outcome of this casting product. You can make the billet, then after that you can machine it, you can roll it, forge it, or extrude it depending on the end application. We also tried the powder metallurgy route. In the powder metallurgy route, you take the elemental powders. You can use that for making nanocomposites as well. And we try to blend it, we try to ball mill it, we try to sequentially ball mill. So we tried three different variation within the powder metallurgy route. After that, we compacted that and sintered it. Now, most of us are aware of traditional sintering using the tube furnace or the Bock furnace, but we also introduce microwave sintering as well. The reason for using microwave sintering is to reduce the carbon footprint, increase the productivity because the heating duration can be reduced by 90%, and the energy consumption can also be reduced by 90%. So it's a wonderful green technology which saves the cost of the end product, in that you take a sample, you put in the microwave under certain specified setup. As you see in this picture here, you have two crucibles here, you have silicon carbide susceptor in between the crucibles, and the heat is contained using the insulation here. You pre-calibrate the microwave for the system, and say, for example, you want to reach 640 degrees centigrade. Our system achieved that temperature in 14 minutes. So you switch on for 40 minutes and switch it off, and your material is sintered. And after that, you can just like do the necessary processing, secondary processing like extrusion, rolling, or forging. Now, while this method is extremely successful for normal materials, we found that the powder metallurgy is very challenging in case of multi-component alloys. We were able to blend it, we were able to compact it, but once it comes to the sintering, no matter what method we used, we were not able to sinter the material properly. It seems to fall apart. The different element that goes in does not like to be sintered for various reasons. But for the disintegrated melt deposition technique, we had all the success we are looking for, and we were able to make multi-component alloy with a density of about 2.25 gram per cc. So apparently, the first composition that we tried was a 5-element composition, contain magnesium containing aluminum, lithium, zinc, calcium, and yttrium. And in the second one, we replaced the yttrium with copper. And let's have a look at the properties. Now, if you look at this property, you see the micro hardness of this material is 237 HV. Now, this micro hardness is more than stainless steel like 304 and 348L, which is a high strength version of 304. And that shows that in terms of hardness, the magnesium based multi-component like can exceed that of steel. That's a potential replacement of the steel, if you can look in that way. If you look at the microstructure, it is always quite interesting for the multi-component alloys with a lot of phases appearing. So as a part of the metallurgical uh, characterization, you have to see how many phases are there. We use the EDS method and we found 5 phases. And when we do the X-ray diffraction method, we found the 6 phases. So that's a part of the protocol when you try to develop a new material. When we replace yttrium with the copper, once again our micro hardness much exceeded that of steels. And in this situation, unlike the previous situation, the microstructure is less complex. And once again, we did the phase analysis, and this material had the less number of phases at 3. And when you do the X-ray diffraction, it is at 4. So basically, what we learned from this thing is that yes, we can make high entropy alloys. The hardness can exceed that of steels, and similar to the white cast iron, these kind of materials can be used in the compressive loading, sliding parts which require high wear resistance and the scratch resistance. Now, since the ductility was still an issue, then we moved on by reducing the number of elements that go in magnesium. Because if you look for structural application in day-to-day application, you need a good combination of strength and ductility. Now, since magnesium is at 1.7 gram per cc, we cannot add too many elements which keep its density to at least around the same or lesser than that of aluminum at 2.7 gram per cc. The second issue with magnesium is that it has a hexagonal closed pack structure, which does not allow it to deform too much. And if you look at the picture below, these are the mostly if you put 5 elements or more, you end up having a reasonably brittle material. So to overcome this limitation, we tried to explore magnesium, aluminum, zinc, copper, and manganese multi-component alloys, which systematically changed the amount of aluminum from 20 to 10. And you see the experimental density in this case reached almost 2.6 in the extruded condition, which is still lower than aluminum, but much higher than that of magnesium. Now, we looked at the microstructure. In the S-cast condition, it was coarse, and you can see the dendrites. And once you extrude it, you can fragment the microstructural feature. And as a result of that, you can expect the properties to go up. Now, if you look at the micro hardness here, 174 at Rockwell B scale, which is still very high. If you look at the yield strength, we are at 282, which makes it suitable for many engineering application, ultimate compressive strength at 500 plus, and we were able to take the ductility to more than 10%. So the basic rule is that if you want to have a reasonable formability, you should be working with a ductility level which is greater than 10%. So this qualifies for that. And if you compare this alloy with the existing alloys, you will see that AZ31B is a commercial alloy which is already used in many applications. The properties are at least double in terms of the yield strength, which lead to the strength-based design. You have the ductility exceeding 10%, and if you look at the specific strength, it is 1.5 times. Now, one of the very high strength aluminum alloys, AL7075, which is used in practically defense application, aerospace application, and many niche application. And this alloy is almost more than 2 times that of uh, the aluminum alloy, and you come with almost like 10 to 20% saving. Now, if you look at the specific yield strength of this high strength aluminum alloy is 39. It is almost one third of that of this alloy. So that makes this alloy attractive for many applications. Then we try to see that whether we can still play with the strength of this material and still can we still look at the lower density than 2.6, which is close to that of aluminum alloy. And you can see the microstructure and its characterization. And what you see is that similar to the previous finding, after extrusion, your microstructure is much more refined. Your micro hardness still reaches a value similar to that of steel. So it is still hard, strong, and scratch resistant. And now if you look at the properties from 280, we are reaching 388 and peak strength of 647 and the fracture strain of more than 11% as in the previous case. And this is much superior to the existing well-used AZ31 and AZ91 magnesium alloys. So these alloys, multi-component alloys, they give you a new avenue to develop new magnesium-based material with high combination of performance. Now, we also try to increase the ductility of this material because ductility means formability. Ductility means you can make more complex shapes. And now in this case, again, we reach almost similar to that of aluminum, but we want to play with the ductility in this case. And you see that orange curve here, which can reach up to like 32% ductility, maintaining still very high value of the strength level. So depending on the end application, you need formability, you need ductility, you go for one composition, you need strength, you go for the other composition. So you can tailor the properties by compositional adjustments. And if you compare that, for example, these values with WE43, which I have highlighted in red. Now WE43 is an alloy which has been approved for aerospace application. Now look at the yield strength. It is twice for this multi-component alloy. Your ultimate compressive strength is almost twice, and your ductility is almost 3 times. So if this works, or if this material qualifies in additional requirement for aerospace application like flammability resistance and the corrosion, the work is pending, then this can be a very easy option to replace the existing alloys, and it gives you much more durability during the application. So in concluding remark, I will like to say that alloy development and microstructural engineering, it's a never-ending process. Multi-component alloy has given a new direction than the traditional alloying method, where we increase the strength most likely by the aging heat treatment. And this multi-component alloy avoid the heat treatment step. Now, high entropy alloy in magnesium is a big challenge because your material can become very brittle. So low and medium entropy alloys, but multi-component are the way to go at this point of time if you need a good combination of strength as well as ductility. Now there are still challenges. There are many challenges because these materials are still new. We need much more high level of microstructural investigation. We have to assess the forming capabilities using Erickson test, and for wide application, we need to have a look at the creep, fatigue, EM shielding, and damping. We need to have a look at the corrosion, weldability, and the tribological response of this material. So with this, I would like to conclude my 20 minutes keynote talk, and I'll be very happy to answer any question that you may have.
questions from the participants?
Good morning to all. I'm Pramod Bingole. I have one question related to this presentation. Uh, First of all, I want to thank to Manoj Gupta sir to given this nice presentation. I have one question related to this multi-component alloys. Uh, is it possible we can cast this multi-component alloy, or what are the drawbacks you are finding into that?
Well, the kind of technique I've used is actually a hybrid of casting and the spray deposition. So it's a liquid phase method. So you can always process by the casting. It's not an issue. Pramod?
Yes, sir. Got it. But
Yeah.
why you have not tried that one? Because it is very easy to easy to adapt that method.
True, but the technique which we have developed at our end, as I indicated, that it's a combination of spray deposition and casting. When you hit it with the argon gas jets, it lead to a much more microstructural refinement. And based on the fundamental principle of material science, if your microstructure is refined, your properties are much better than the casting rule. So if you process the same thing without disintegration by gas jets, you may have problem with having not as good property as we are seeing, but it is possible.
Okay, sir. Thank you, sir, for
Yeah,
your guidance.
yeah,
Thank you.
Excuse me, sir.
yeah,
Myself, Dr. Pankaj Kumar Singh from IIT BHU.
yes.
Your presentation was nice. My question is that in regarding to the magnesium research, do you have gone through some gold or silver nanoparticles also with the magnesium?
Not really. Gold and silver are both expensive items. Silver people are trying to put in there because if you're targeting for biomedical application, then silver works as a antimicrobial or anti-infection agent. But at the end of the day, if you want to develop an alloy and you want in the engineering application, which reach to a common man, you don't want your material to be expensive. So you want a material which is not expensive, unless for biomedical application, which is in that people have tried up to 1% of silver, but not as a particle because most likely it may end up dissolving. I have to look at the phase diagram to see the mutual solubility of magnesium and silver to ensure whether it can stay as a particle or it goes as a alloying element. Are you there, Pankaj?
Thank you, sir.
Yeah.
Any other questions?
Hello, sir. Hello.
Yes, Morley. We can hear
Yes,
you.
sir. Okay, sir. This multi-component alloy you are telling, no?
Yes.
What is it? Yeah, yeah, alloy means what kind of combination of the alloy you have been done for this one?
Well, you have seen the composition I've presented. So we have
Yeah.
tried many composition. You can try, for example, aluminum, lithium, zinc, manganese, yttrium. So these elements you have to add into certain combination. Now, how we arrive at that composition is through a lot of literature search, through investigation of the binary phase diagram, and a bit of the hit and trial also to see that which system works and which system does not work.
Okay, sir. But what kind of the biomedical application you are it will have that one, sir?
Biomedical application is quite well set for magnesium based material. I'm going to give a keynote on September 1st. You should attend that. But in brief, there are implants which are called as the temporary implants. In that, for example, if you have a crack in your bone or a slight fracture in your bone, normally people put the steel nails in there, and once the
Yeah.
bone is healed, then they take a second surgery and remove them because otherwise they will become toxic over the time. So in this situation, what you do is that you put the magnesium based material inside there, and you don't have to take it out because magnesium is a nutritional element and it resorbed by the body over the time. So you avoid the second surgery, you save the doctor cost, you save the patient trauma, and all the associated issues that comes with the second surgery. So that is where you use the magnesium based implants. Like it has been already been marketed for stents, for example, in the cardiovascular application, and also available by some people as a compression screws. So it is, the market is rapidly growing at this point of time. So temporary implant is a keyword.
Thank you. Sir, can you send this PDF or anything, sir, for us to something we'll have.
Yeah, you just
PDF.
listen. Yeah, I
Yeah.
will be talking a bit more and in a bit more explanatory way on my September 1 talk, which is 1 hour talk. So you must attend that first.
Okay. Thank you, sir.
Yeah, yeah.
I thank Dr. Manoj Gupta for delivering the keynote of that. I welcome the PR Ashok Sethi, Vice President, National Education Society.
Yeah.
And I request him to speak a few of the words about the work. Dr. Manoj Gupta, ವಿಶ್ವೇಶ್ವರ ಕಾರ್ಯಕ್ರಮವನ್ನು ಸಫಲ ಹಾಗೂ ಕೆಲಸದಲ್ಲಿ ಪ್ರತಿ ದಿವಸ ಹೊಸ ಹೊಸ ಕ್ರಮಗಳನ್ನು ಹುಡುಕ್ತೇವೆ ತಕ್ಕಂತೆ ನಾವು ಹೋಗಲೇಬೇಕು. ಮುಖ್ಯವಾಗಿ ಇವತ್ತು ಸಬ್ಜೆಕ್ಟ್ ಉತ್ಸಾಹ ಸಾರ್ವಜನಿಕ ಉತ್ಸಾಹ ಆಗುತ್ತೆ, ಆತ್ಮದ ತುಂಬ ಉತ್ಸಾಹ ಆಗುತ್ತೆ ಅಂತ ಅವ್ರಿಗೆ ಗೊತ್ತಿರುತ್ತೆ. ಇವತ್ತು ಬಹಳ ಹಿಂದೆ ಆರ್ಥೋ ಪತ್ರಿಕೆಗಳಾಗ ಆರ್ಥೋ ಏನೋ ಬೆಳೆಗಳಲ್ಲಿ ದೊಡ್ಡ ದೊಡ್ಡ ಭಾರವಾದ ವಸ್ತುಗಳು ಬರ್ತಾ ಇದ್ರೆ ಕಷ್ಟ ಆಗ್ತದೆ. ನೀತಿನ ಬಹಳ ಲೈಟ್ ಆಗಿರೋದ್ರಿಂದ ಮತ್ತೆ ಏಕೆ ಬದಲಾಗುತ್ತೆ ಬಹಳ ಮುಖ್ಯವಾಗುತ್ತೆ. ಮುಂದಿನ ದಿನಗಳಲ್ಲಿ ಸಾಮಾನ್ಯ ಕೂಡ ಅರ್ಥಗಳು ಬರುತ್ತೆ. ಹಾಗಾಗಿ ಅದು ಒಳ್ಳೆ ವಿಷಯ. ಮುಖ್ಯವಾಗಿ ಇನ್ನೊಂದು ಬಹಳ ಮುಖ್ಯ ಇದೆ, ಆರೋಗ್ಯ ದೃಷ್ಟಿಯಿಂದ ಯೋಚನೆ ಮಾಡೋದಾದ್ರೆ ಆರ್ಥೋ ವಿಷಯಕ್ಕೆ ನಿಜವಾದ ಇವತ್ತು ರಾಜ್ಯಗಳು ಕಾಲಿನ ಕೈಗೆ ಆರ್ಥೋದಲ್ಲಿ ಬಹಳ ಸಮಸ್ಯೆ ಬರ್ತಾ ಇದೆ. ದೊಡ್ಡ ದೊಡ್ಡ ರಾಟಗಳು ಆಗ್ತಾ ಇದ್ರು ನಮ್ಮ ಉದ್ಯೋಗ ಆಗುತ್ತೆ ಕೂಡ ಕರ್ನಾಟಕ ಬಹಳ ಹಿಂದಿನ ದಿನಗಳಲ್ಲಿ ನನಗೆ ಗೊತ್ತಿರೋ ಪ್ರಕಾರ ಅಬ್ದುಲ್ ಕಲಾಂ ಅವರು ಹೀಗೆ ಆರ್ಥೋದು ಕಾಲು ಫ್ರಾಕ್ಚರ್ ಆದಾಗ ದೊಡ್ಡ ದೊಡ್ಡ ಕಬ್ಬು ಹಾಕ್ತಾ ಇದ್ದಾಗ ಆ ಮಕ್ಕಳಿಗಾಗಲಿ ದೊಡ್ಡವರಾಗಲಿ ಹಾಕೊಂಡು ಓಡಾಡೋದು ಕೂಡ ಕಷ್ಟ ಆಗ್ತಾ ಇತ್ತು. ಯಾವುದೋ ಹಾಸ್ಪಿಟಲ್ ಹೋದಾಗ ಅಬ್ದುಲ್ ಕಲಾಂ ಅವರು ನೋಡಿ ಬಹಳ ನಂಬಿಕೆವಾಗಿ ಫಸ್ಟ್ ಅವರು ಇದು ವಿಜ್ಞಾನಿ ಆದಾಗ ಮೊಟ್ಟ ಮೊದಲ ಕಾರ್ಯಕ್ರಮ ಮಾಡಿದವರು ಅವ್ರ ನೀರು ತೆಗೆದು ಪೆಟ್ರೋಲಿಯಂನ ಉಪಯೋಗಿಸುವ ಮಾಡಿದ್ರು. ಸ್ವಲ್ಪ ಅಗೌರವಾಗಿತ್ತು ಅವಾಗ. ಇದು ಮುಂದುವರೆದ ಈಗ ಮ್ಯಾಗ್ನೇಷಿಯಂ ಹಾಕ್ತಾ ಇರೋದು ನಿಜವೂ ಬಹಳ ಇದ್ರ ಬಗ್ಗೆ ನಮ್ಮ ಮುನ್ನೋಡಿ ಸುತ್ತಾರು ಸ್ಟಡಿ ಮಾಡಿದ್ದೇನೆ. ಸಾರ್ವಜನಿಕ ಉದ್ಯೋಗ ಆಗುತ್ತೆ. ಈ ಕಾರ್ಯಕ್ರಮ ನಮ್ಮ ಬೇರೆ ಮಾಡ್ತಾ ಇರೋದು ಹೆಮ್ಮೆ ಅನ್ಸುತ್ತೆ. ನಾನೊಂದು ಇದು ಕೂಡ ನಮ್ಮ ನಾನು ಕೂಡ ಜೈನಿಕ ಬಗ್ಗೆ ಗೊತ್ತಿದೆ ಅಂತ ನಾನು ಅನ್ಕೊಳ್ತೀನಿ. ಬಳ್ಳಾರಿ ನಮ್ಮ ಜೈನಿಕೆ ಒಳ್ಳೆ ರಾಷ್ಟ್ರೀಯ ನಮ್ಮ ರಾಷ್ಟ್ರೀಯ ಶಿಕ್ಷಣ ಸಮಿತಿ ಪ್ರಾರಂಭ ಮಾಡಿದ್ದು ಯಾವಪ್ಪ ಅಂದ್ರೆ ದೇಶಕ್ಕೆ ಹೋರಾಟದಂತ ಮನುಷ್ಯರು ಪುಣ್ಯಾತ್ಮರು ಇದನ್ನು ಪ್ರಾರಂಭ ಮಾಡುವ ಸಂಸ್ಥೆಗಳು ಈ ಒಂದು ಸಂಸ್ಥೆಯಲ್ಲಿ ಕಾರ್ಯಕ್ರಮ ಮಾಡ್ತಾ ಇದ್ದ ಬಹಳ ಮುಖ್ಯವಾಗಿ ನಾನು ನಮ್ಮ ಸಂಸ್ಥೆಯಿಂದ ಪರವಾಗಿ ಎಲ್ಲಾ ಡಿಪಾರ್ಟ್ಮೆಂಟ್ ಪ್ರಾಂಶುಪಾಲರು ಜೈನಿಕ ಎಲ್ಲ ನನಗೆ ಅವಕಾಶಕ್ಕೆ ನಾನು ಮಾಡ್ಕೊಂಡಿದ್ದೇನೆ. Now invite Principal of JNMC, Dr. Manjulata P, to deliver the presentation.
Respected dignitaries, all for the knowledge of 1 week speaking on novel manufactured magnesium-based alloys for industrial and biomedical applications. Chief guest of today's function, Dr. Manoj Gupta, in Singapore. Guest Persona President, Sri S.N. Narayan, Secretary, Sri S.R. Narayan Petty, Vice President, Sri C.R. Narayan, Secretary, Treasurer, Dr. N.M. Secretary, Lead Infrastructure and Coordinator, FDP, Dr. V. Basuraj, Professor and Head, Mechanical Engineering, faculty members and participants. First of all, I would like to congratulate the scientific department and the coordinator of the M.M. Secretary for arranging this event. I also thank AICT for supporting this FDP by sanctioning the financial grant. And coming to the topic, already we had a keynote address about this topic delivered by our speaker. Also, previous topic fund. And coming to the few points, magnesium and its alloys are used in automotive applications and primarily also used in health and biomedical industry like so and cardiovascular. Dear participants, as per the schedule, excellent speakers from IIT, MIT, and industry from the concerned areas invited for this FDP. I request all the participants to utilize this opportunity. This is the best opportunity to enhance our knowledge by attending the FDP. So with these words, I will conclude my speech. Wish you all the best. Thank you, sir. To conclude this inaugural function, I invite Deepak sir to render a vote of thanks. Good morning to all. It gives me immense pleasure to deliver the vote of thanks for this inaugural function on the foundation of the program. My very special thanks to Dr. Manoj Gupta, Associate Professor, National University of Singapore, who honored us with keynote address on the one-week inaugural program. I take immense pleasure in extending my sincere thanks to Sri A.S. Vishwanathan, President, National Education Society, Shimoga, for breaking his presence and sharing his inspirational thoughts for this program. I also take immense pleasure in extending my sincere thanks to Sri Ashwat Narayan Shetty, Vice President, National Education Society, Shimoga, for creating his presence for this inaugural program. I extend my heartfelt thanks to Sri S.N. Nagaraja, Secretary, National Education Society, Shimoga, for his enormous support and his insight on this inaugural FDP program. I would also like to take this opportunity to express our heartfelt thanks to Sri Amaringa Kirti, his absentia, Joint Secretary and National Education Society, Shimoga, for his enormous support for organizing this program. I would also like to thank Sri C.R. Nagaraja, Treasurer, National Education Society, Shimoga, for gracing his presence and sharing his thoughts on this inaugural function. I'm very happy to extend a sincere thanks to Dr. Manjunatha P., our principal, JNN Shimoga, for delivering the presidential address for this inaugural program. I would like to take this opportunity to thank Dr. M.M. Rajat Hegde, Professor and Dean of Infrastructure, JNN Shimoga, for his with the inaugural function. I would also like to thank Dr. E. Basuraj, Head of the Department of Mechanical Engineering, JNN Shimoga, for welcoming the challenge. Finally, my heartfelt thanks to Mr. Parameswaran, Mr. Pradeepa MD, and Mr. Subhash Bunker and their team for their efforts in ensuring this inaugural program successful. Thank you all. Dear participants, join the session 2, that is technical session 1. Now, the exact point, 11.9.